We will be beginning on page 578 in your books, section 11.1, Simplifying Radicals. You do need to follow along with your handout guided notes and make sure that you copy down the examples and do the check understanding as they're assigned. So the first thing we're going to talk about is the term radical expressions. So radical expressions include a radical, which is your square root sign that you're accustomed to seeing. The examples that they show us here are the expressions 2 square root of 3, and then this expression here would be read the square root of the quantity x plus 3. And when you hear that word quantity, that indicates that the entire next part of that, x plus 3, is included in the radical. The first property we're going to look at is the multiplication property of square roots. This property tells us that if we have a square root of two numbers that are multiplied, it can be broken up with one radical times another. It also goes the other direction. If you have two radicals that are being multiplied, then you can multiply what's inside the radical and go the other way as well. The example that they give us here is the square root of 54. That square root can be broken up into the square root of 9 times the square root of 6. Now this helps us because we can see that 9 actually has a square root, which is 3. 6, however, does not have a square root, so you'll notice that is left in the radical like we did in the prior section. So we can simplify the square root of 54 to be 3 times the square root of 6. So let's look at example 1 to see how that helps us simplify square roots. Now there are two ways to simplify square roots. The first way is to look for a perfect root inside a radical. So they have given us this example of 192. Now, I will say that if you can see a perfect radical, this is a very easy way to do this. And so in looking at this, they're telling us that 192 is actually the product of 64 times 3. And so if you know that you have a perfect root in there, then you can say, well, we just looked at the property that tells us I can break that up to be the square root of 64 times the square root of 3. I know that 64 has a perfect root. The perfect root of 64 is 8. So I end up with 8 times the square root of 3, which is how you would simplify the square root of 192. Now the problem here is that with a number like 192, you may not always see the perfect root. And so another way to do it is to use your factor tree. Now this is a method that you would have used to break apart numbers probably in middle school. So we're going to go over it. So if I have 192, then I want to look for the smallest prime number that goes into 192. Now remember, prime numbers are numbers that can only be divided by themselves and 1. So the smallest prime number that I think of when I look at 192 is actually the number 2. And so if I divided this by 2, 19 is where I would start. So 19 divided by 2, well, that is 9. And I have a remainder of 1. And then 12 divided by 2 is 6. So this is the beginning of the factor tree. 192 can be broken up to 2 and 96. And then I'm going to keep going until all I have are primes. So I look at 96 and I say, well, what number can go into 96? And it's an even number, so once again, I know that 2 will go into it. And I have 9 divided by 2. Well, that is 4 with the remainder of 1. And so then I have 16 divided by 2, which is 8. And then once again, 48 is not a prime, so I can keep going. And the smallest number that goes into 48, it is an even number, so I'm just going to start with 2. And I have 4 divided by 2, which is 2. And then I have 8 divided by 2, which is 4. And I can keep going because 24 is not prime. It's even, so we know it is divisible by 2. 24 divided by 2 is 12. So 2 times 12 is 24. 12 is divisible by 2. 2 times 6. And then 6 is divisible by 2. 2 times 3. And so this is what's called a factor tree. I am breaking 192 into prime factors. And you would have done this when you learned like exponents. You would say, oh, well, that's 2 to the 6th power times 3. But for this case, we're actually going to do it to figure out what the radical is. Because I may not look at 192 and just automatically know that 64 and 3 make up 92. And so when you do this factor tree, you keep breaking it down until you have all prime numbers. And then because we're doing the square root, we are looking for numbers that pair up. So I'm going to say, well, every time a number pairs up, so 2 and 2, then that can come out of the radical. Since we're looking for the square root, it can come out of the radical. So this group right here, that's 2 of my 2's, that can come out of the radical. And then I have another pair of 2's. That can come out of the radical. And I'm going to multiply those, so times 2. And then I have another pair of 2's. That can come out of the radical. And I have a 2 there. Well, the 3 does not have a 3 to go with it. It does not pair up. And so that number cannot come out of the radical. And so the 3 will stay in. So I had a group here that came out as a 2, a group here that came out as a 2, and a group here that came out as a 2. You'll notice for every 2 numbers that pair up, I take it out 1 time. So I took it out 1, 2, 3 times. Once you take it out, anything that comes out is multiplied together, and anything that stays in is multiplied together. So I have 2 times 2 times 2, which gives me 8. And then I have the square root of 3, which doesn't come out, square root of 3. And you will see that that is what I got when I did it, looking for a perfect root. And we're going to do several of these to learn and remember how to do perfect roots and how to do factor trees. So I'd like you to try check understanding 1, A, B, and C at the bottom of page 578. Okay, first review your answers and check your work, and then we're going to go over each one of these. For square root of 50, you should have gotten 5 square root of 2. For negative 5 times the square root of 300, you should have gotten negative 50 square root of 3. And for the square root of 18, you should have gotten 3 square root of 2. So let's go over each one of these. Let's start with A. I have the square root of 50. And so if you notice that had a perfect root, you may have known that that's 25 times 2. And so you have the square root of 25 times the square root of 2, which is how we get 5 times the square root of 2. Now, if you did not know that there was a perfect root, then you can use your factor tree. And you can really use any numbers that you want. If it's easier for you to look at this and say, well, 5 goes into it and 5 is prime, then you could say, well, that's 5 times 10. And you can see that 5 goes into 10 again, so 5 times 2. And now you can see all of these numbers are prime numbers. And so we're done with our factor tree. And then we are looking for numbers that pair up. And one way I like to say, if you remember, if it has a date, it comes out. If it is single, it stays in. And so in this case, we had a pair of 5s, so we take 1 5 out for every 2 that are in there. And then we have a 2 that does not have a pair. It stays in 5 square root of 2, which is the right answer. All right, let's look at the next one. For this one, we have -5 square root of 300. And if you knew that this had a perfect root, that's -5 times the square root of 100 times the square root of 3, which is how we get -5 times the square root of 100 is 10 times the square root of 3. And that is how we would get -50 on the outside. Square root of 3 stays on the inside. Now, if you did not know that, then you are going to do your factor tree, 300. And you can see 3 and 100, 2 and 50. And you can divide 52 and 25. And 25 would be 5 and 5. And so doing the factor tree, again, you're looking for a prime number that goes into that number and you're dividing it out. Now, I'm going to look for what pairs up. Well, 3. 3 does not have a pair. There is no other 3. So that one cannot come out. 2, that does have a pair. So I can actually take out 1, 2 for that pair. And then 5 does have a pair, and so I can take out that 5. Well, I already had a -5 on the outside. So I have -5 that was already there. I took out a 2, so that goes here. And I took out a 5, so that goes here. The 3 could not come out, so that stays in. And then I just multiply. -5 times 2 is -10, times 5 is -50, square root of 3, which is my answer. Now let's look at the last one. For 18, square root of 18. Now again, you may have seen that that is the square root of 9 times the square root of 2, which is where we get 3, square root of 9. 2 does not have a root, square root of 2. But once again, if you did not recognize that perfect root, you can factor 18. Factors of 18, we're going to start with a prime. Well, 2 goes into 18, which is 2 times 9. For 9, 3 and 3. And those are all primes, so we're done. We're going to look at what has pairs and what doesn't. 2 does not have a pair, so it has to stay in. 3s, there's 2 of them, so I can take out 1, 3. When I do that, the 3 will come out, the 2 will stay in, which is my answer. Now let's look at the top of the next page for example 2. Now the difference between this example and the other one, you will notice, is that it has a variable. And so I like to treat the variable the same way. There are actually 2 different ways to do this, and I'm going to show you both of them. So 45, again, you may notice that 45 has a perfect square in it, which is 9 times 5. And so the 9 square root of 9 times the square root of 5 gives us 3 and square root of 5. However, we now have this a to the 5th. And so if you look at a to the 5th, if we break this up almost like a factor tree, there are 5 a's. 1, 2, 3, 4, 5. Which means we have a pair here, which lets us bring out an A, and a pair here, which lets us bring out an A, and then we have this A, which does not have a pair. So that means I already have my 3 times my a that I can pull out, times my a that I can pull out. And then I have a 5, which is staying in the radical, and I have this other a that is staying in the radical. And I would say 3 times a, well, that is a squared. And on the inside, I have 5a. So that actually is my answer. Another way to look at these, a to the 5th, is it will always be 2 that we're looking for. So I can take my 5 and I can divide it by 2. Well, 5 divided by 2, don't think fractions. Think when you did division a long time ago. You had an answer and a remainder. So 2 goes into 5 2 times with a remainder of 1. This 2, how many times it goes in, will always represent the variables on the outside. And then the remainder will always represent the variables that are on the inside. And so you'll notice that I had 2, which are how many a's I had on the outside, and then I had 1, which is how many a's I had on the inside. And so you can either break it up like this and just write them all out and count how many pair up and how many don't, or you can use this division technique where how many times it goes into it, and think about the fact that if it goes into it 1 time or 0 times with remainders, and then remainder, how many times it goes in, comes out, remainder stays in. So go ahead and try check understanding number 2, A, B, and C at the top of page 579. All right, let's look at these together. First, check your answers, and then we will go through them. The square root of 27n squared should be 3n times the square root of 3. Negative a times the square root of 60a to the 7th should be negative 2a to the 4th, square root of 15a. And then the square root of x squared y to the 5th should be xy squared times the square root of y. So let's look at these 3. For 27n squared, let's look at the number first. 27, well, the prime number that goes into that would be 3 times 9. And then, of course, 9 would be 3 times 3. And so if I group it, we can take a 3 out. So a 3 will go on the outside. And then this 3 right here does not group, so it is going to be on the inside. And then let's look at our variable. We have n squared. If you split that up, n times n, or if you did the division, 2 divided by 2, you're always dividing by 2. That's going to be 1 with the remainder of 0. So that means if I did it the top way, n's paired up, so an n came out, and no n's were left alone, so no n's remained in. That's my answer. If I did it the division way, 1 n came out, no n's stayed in, which is how I get my final answer. Let's look at the second one. All right, for this one, I have this negative a on the outside, so I automatically know that that's going to be out there. And then I'm going to use my factor tree for the 60. So for 60, I know that it's divisible by 2 because it's even, so 2 and 30. 30 is also divisible by 2, 2 and 15. And 15 is divisible by 3, 3 and 5. And this is prime. So now I'm going to look for what pairs up. These 2's pair up, so I can take a 2 out. The 3 does not pair up. The 5 does not pair up. So both the 3 and the 5 will stay in. And then if I look at my variables, I have a to the 7th. All right? And so if I use my division method, 7, we always divide by 2. 2 goes into 7 3 times with the remainder of 1, which means 3 of my A's go out and 1 of my A's stay in. And so when you simplify this, you're going to multiply everything on the outside. So I have a negative on the outside, and then I have this 2, and then I have a times a cubed. Remember, you add your exponents here, so that's a to the 4th. I have 4 a's. And then on the inside, I have 3 times 5, 15 times a, which is where I get the negative 2a to the 4th square root of 15a. Let's look at the last one together. So for the last one, I just have variables. So if I look at the x squared first, I do 2 divided by 2. Well, that is 1 with the remainder of 0. And then if I look at the y to the 5th, I have 5 divided by 2. 5 divided by 2 is 2 with the remainder of 1. And so for my x's, 1 x will come out and 0 x's will stay in. For my y's, 2 y's will come out and 1 y will stay in, which is where I get my answer xy squared times the square root of y. Let's look at example 3. Now in this case, I am multiplying 2 radicals, all right? And so when you multiply them, you just multiply the outsides and multiply the insides. But then you want to simplify it. So for this one, they give us 8 times 12. Well, 8 times 12 is 96. So the square root of 8 times the square root of 12 is the square root of 96. Now, once again, if you see that there is a perfect root, which they tell you this is the square root of 16 times the square root of 6, then you can simplify it for square root of 6. But most of the time you will not see that. So you want to use your factor tree. Now here's the key. When you're multiplying these, you already know that 8 times 12 equals 96. So you can actually start with 8 and 12 if you want to. And so if you are doing this, you may want to just start with those numbers that you know, because you've already done that, like you already did that. And you don't even have to multiply it to get to the 96. You can literally start with 8 and 12. And we know that 8 simplifies to 2 and 4, and then to 2 and 2. And we know that 12 simplifies with 2 and 6 and 2 and 3. Now, while it seems like this is 2 completely factoring, it's all part of the factoring of 96. So anything in any of these numbers here can pair up. It doesn't matter if it came from this side and that side. You can pair up any of these numbers. And so we're going to group these numbers here. We're going to say, well, 2's group here, that's a 2. 2's group here, that gives us a 2. So we have a 2 here that now does not have another group, and a 3 here that does not have another group. And so we're going to look at what we took out. We took out 2 and 2. And we left in a 2 and a 3. And so remember, we simplify it by multiplying. 2 times 2 is 4. Inside, we have 2 times 3, which is 6. So we have 4 times the square root of 6. And that's the same answer as if you had seen that 16 was part of that when you multiplied. Let's look at B. Now for B, we have numbers on the outside. And so this 3 and this 4 need to be multiplied. That's going to be 12. And on the inside, we have 2b times 10b, which means if we multiply those, we have 2 times 10, which is 20, and b times b, which is b squared. And so now if we use our factor tree, we already know that's 2 and 10, and 2 and 5. And so on the outside, we're going to have this 12, which was already there. These 2's pair up, so we can take a 2 out. This 5 does not have a pair, so it stays in. For the b, we have b squared. If we use the division technique, 2 divided by 2 is going to be 1 with a remainder of 0, which means we have 1 b that comes out and no b's stay in. And so when we simplify that, we're going to say 12 times 2, which is 24, and we have that b. And then inside, we just have that 5. So our answer here would be 24b times the square root of 5. So go ahead and try check understanding 3, which is in the middle of page 579, A, B, and C. So the first thing we're going to do is we're going to check the answers, and then we're going to go over each one of those. The square root of 13 times the square root of 52, you would have gotten 26. 5 square root of 3c times 6 square root of 6c is 15c square root of 2. And then 2 square root of 5a squared times 6 square root of 10a cubed is 60a squared times the square root of 2a. So let's look at these three together. For the first one, in this case, instead of multiplying 13 times 52 and getting this huge number, I'm just going to say, well, this is 13, whatever number this is. We know that it is 13 times 52. Those are going to be the first two numbers in my factor tree because I know that I'm about to multiply those. Well, 13 is already prime, so I'm going to start with the 52. 52 is even, so I know it is 2 goes into it. 2 goes into 5. 2 times with a remainder of 1. 2 goes into 2, 12 6 times. So 52 is 2 times 26. I know that 26 is also even, so I can divide that by 2. 2 and 13. Well, now I have all primes. So I'm going to look for what pairs up. Well, the 2's pair up, so I can take a 2 out. And these 13's also pair up, so I can take a 13 out. Well, I don't have any numbers left on the inside, so I just multiply these two, which gives me 26. Nothing left on the inside, so that is my answer. Let's look at the next one. So for the next one, I know I have a 5 that's going to be on the outside. So I'm going to go ahead and put that there. Now I'm going to look at the 3c and the 6c. Now you may have multiplied these because that's not a huge number, and you would get 18. And then you would have a c squared for the c's there. C times c is c squared. Now when you go to do this factor tree, you already know that 18 is 3 times 6. And then of course you know that 6 is 3 times 2. And so when I do that, my 3's pair up. So that means I'm going to have a 3 on the outside. And my 2 does not have anything to pair up with, so that is on the inside. And then for my c's, if I do my division method, 2, I'm using that exponent, 2 always divided by the 2 is going to be 1 with a remainder of 0, which means I have 1 c on the outside and I do not have any c's on the inside. To simplify that, I multiply. 5 times 3 times c is 15c, and on the inside I still have my 2. Let's look at the last one. For the last one, I have 2 numbers here on the outside. I have 2 times 6, which is automatically on the outside. 2 times 6 is 12. On the inside, I have 5 times 10, and you may have multiplied that. 5 times 10 is 50, and I have a squared times a cubed. Well, we add those exponents, so I have a to the 5th. So let's look at our 50 first. Well, we already know that 50 is 5 times 10, because those are the numbers we use to get it. And for 10, well, 5 goes into 10 again, so 5 times 2. Well, now I have all primes, so if it pairs up, it comes out. The 5's pair up, so that comes out. And then inside the radical, the 2 does not pair up, so it goes in. For my a's, I have 5 a's. 5 a's, I'm going to divide by 2. 5 divided by 2 is 2 with the remainder of 1. So 2 of my a's come out, a squared. 1 of my a's will stay in. And then I'm going to simplify by multiplying. 12 times 5 is 60 times my a squared. That's on the outside. And then on the inside, I have 2a. Homework. So over the weekend, you need to do pages 581 to 582, numbers 1, 9, and 21.